Hello there, welcome to the second video about an obstacle problem for the p-elastic energy, and we are going to see what we did in the last video, or first recall what we did in the last video, and then we are going to finish the proof that we gave there of the non-existence for large cone obstacles by a non-degeneracy result that I still owe you. But first of all, let's recall what was the variational problem that we considered. So we have an elastic energy which arises from integrating the curvature of a graph to the power of p. And we are only looking at graph curves that come from a suitably smooth function from the interval 0, 1 to the real numbers. P is between 1 and infinity. And we seek to minimize the following energy. So this is the energy that you get if you write that all out, what the curvature is and stuff. Among all u and w to p that have fixed ends and that lie pointwise above an obstacle function psi, and on the obstacle function require that it's continuous, that it's non-trivial, and that it's not present at the boundary of the interval that we are considering. So the admissible set then is basically M of psi, which is the set of all u and w to p that have those fixed end condition and that lie pointwise above the obstacle. And our goal is now to show the following non-existence result. So if psi of 1/2 is bigger than some h star of p, which is explicit and also sharp, then there does not exist a minimizer u star in M of psi. So this is what we want to show, and h star also had a geometric interpretation, at least for p equals to 2. We know that from the last video. And h star of p will also have a geometric interpretation, which we will recall soon. So first of all, one should say each minimizer is concave, each minimizer is C2, and the second derivative vanishes at the boundary, which is also equivalent to saying that the curvature vanishes at the boundary, since the obstacle is not present there, and therefore the minimizer doesn't want to curve unnecessarily at those points. And such minimizer is a critical point, so a solution of the Euler-Lagrange equation wherever the obstacle is not touched. And globally, one can say that it's such a super solution. So if you perturb with a positive function, then the derivative takes also positive values there, basically. So this is something that we will use that we haven't used in the last video, but it is definitely important to recall it here since we will use it heavily. Maybe first of all, one could think maybe one cannot even learn so much from this equation, because if the energy is second order, then the Euler-Lagrange equation don't look too much at those terms, like there's no point in looking at them very detailedly. But it's just like this is going to be a fourth order equation that comes out from there if you integrate by parts. And it's also, as we already discovered, degenerate elliptic. So maybe it is at this point unclear why one should be able to learn very much from this, since one has no maximum principle available and one has losses of regularity because of the degeneracy. So it's not clear what to do with this equation, but we will see that it can be of use later, since we will make a good substitution for this equation, basically. If psi is a symmetric cone obstacle, that we also discovered, so if psi looks like so, so this is the picture that I wanted to show there, then each minimizer satisfies that the minimizer can touch the obstacle only at the tip. In particular, this u star is a critical point everywhere except for 1/2, since now this set is just 0, 1 without only this 1.1/2. And this makes it very easy. So this insight about symmetric cone obstacles makes it very easy to describe minimizers, since you just have to combine two critical points, one between 0 and 1/2 and one between 1/2 and 1. And this leads to the question of how the critical points can be classified. And last time we got 3 possible types of critical points, namely such an inflectional p-elastica, so a wave type curve and pieces of that, and scalings and rotations of those pieces. That could be possible, a possible critical point. Another possible critical point could be lines. And now, because of the degeneracy, I have a problem basically in this case where p is not equal to 2. Namely, I could also get type 3 critical points, which are mixtures of those 2 critical points. Because of the degeneracy that we discovered last time, it might be possible to mix those 2 types of critical points and make a new critical point out of this mixing procedure. And this is a problem basically, since then we have very many critical points that we cannot really deal with, or that deter us from repeating the proof that Tatsuya Miura gave in the case of p equals to 2. Remember the one that I showed you in the last video. So what is really important for today is that we have to exclude those mixtures of type 1 and type 2 critical points. So basically, you have to rule out those configurations where you mix the inflectional elastica with the line. So this happens here. And basically, at this point, we have no reason to rule it out, because also what we know is that the degeneracy of the equation happens exactly at points where the curvature vanishes, and this happens exactly here. So basically, it is difficult to rule them out just by looking at the equation, and this is because of the degeneracy. So we will have to come up with some non-degeneracy result. And here's the non-degeneracy result that I also showed you in the last video. So if we have a minimizer, then the second derivative is smaller than 0 on 0, 1. So the minimizer is strictly concave. And because of the strict concaveness, it is impossible to take pieces of the critical type 3 critical points like this, because they satisfy u prime prime equals 0 whenever a line part is taken and rotated appropriately. So basically it is impossible then to take type 3 critical points. So all that remains to show is this theorem. And how do we prove this theorem? Basically, we make a substitution. We look at this second order quantity w star, which is negative u star prime prime of x to the p minus 1 over some nonlinear denominator, which we have to choose in a careful way. And we will see why we chose it that way later. So this substitution here satisfies basically w star is greater or equal to 0, right? Because we already knew that u star prime prime is less or equal to 0, since u star must be concave. And we already know also, because the curvature vanishes at the boundary, that basically this holds, so this w star vanishes at 0 and 1. So this is the quantity we study there, and this quantity will hopefully tell us something about the behavior of u star. At this point this is not clear, because it is only a second order quantity that only might tell us something about u star prime prime, so we'll see. And what one can derive there, and we will later see how it can exactly be derived, w star lies in w1 infinity. And the reason for that is basically that the Euler-Lagrange equation takes a very easy form in terms of w star. Namely, so it is like the derivative of the energy is some positive function, positive c1, multiplied with W star prime times phi prime. This one can see. And this is great, since if you now integrate by parts here in this equation and shift the derivative of the phi to the rest, you get a second order elliptic operator, negative d over dx of a positive function, so a positive matrix here, but it's only one times one matrix, times the derivative of W star. And this makes, therefore, this derivative is a second order elliptic operator in terms of W star. And this is really great, because then we have maximum principles that we can actually use in order to describe the behavior in terms of W star. So this is actually what is our great advantage here. And this substitution, in the case of p equals to 2, it was already known to Euler, and this is why it now carries the name Euler substitution, and we will see what it helps. So we will now prove this non-degeneracy result. So we have to prove that u prime prime is smaller than 0, strictly smaller than 0 on 0, 1. So how do we do that? Instead, or equivalently, one could probably prove that W star is bigger than 0 on the interval of 0, 1, and this we will prove. And so recall the elliptic equation for this W star, and recall also, because U star is a minimizer, so we have a super solution property here. This is what we will use now. And what does it now mean to be a super solution? In a weak sense, this equation yields the following. If I integrate by parts formally, then I get that this second order elliptic operator is bigger or equal to 0, and W star of 0 equals W star of 1 equals 0. And I remark the second order elliptic operator has no zeros order coefficients, so all maximum principles that I want can basically be used there. Let us also recall that W star is bigger or equal to 0, so 0 is the absolute minimum value it can actually take, and it will take at 0 and 1, right? And now one could use the strong maximum principle. The strong maximum principle says if a minimum is attained in the interior, then the function needs to be constantly the minimum. So either the minimum is not attained, which accounts for W star being bigger than 0 on 0, 1, or the minimum is attained, but then W star needs to be constant, and the only constant that is available is the constant 0. And this is exactly what we wanted, since now W star has basically exactly the opposite sign of U star prime prime. That one can see by the definition of W. And that way we obtain like this result. Either U star prime prime is less than 0 everywhere, or U star prime prime is identically equal to 0. So this one can actually get with the strong maximum principle since basically 0 is the absolute minimum value of W star, and this is why we get that here. I have to say you something here, which we will talk about in the very end of the talk. So I'm now applying the strong maximum principle to a weak solution. And one can of course ask if that is actually allowed. So as much as we know about the strong maximum principle, it's maybe only applicable to like pointwise solutions. So if you repeat the standard proof of the strong maximum principle, it is maybe only applicable to more regular settings, where this W would have to be in C2, which is actually not true for those obstacle problems. So we really have to be careful here. It's at maximum in W1 infinity, and therefore, or it could be more regular, but one knows this regularity is optimal, so one can find an obstacle such that it is in W1 infinity. And yeah, so therefore we might have to talk about the fact whether the strong maximum principle is applicable here or not. But we will do that later. Let us first finish the proof. So I have now two possibilities. Either u star prime prime is less than 0, the case which I wanted, or u star prime prime is identically equal to 0, but if it's identically equal to 0, then u star must be a line, and therefore u star must be identically equal to 0 because of the fixed boundary values at the boundary. Okay, so, and this is not happening basically because u star needs to lie above the obstacle, so that is impossible. Okay, so this was the proof there. So we have proven now the non-degeneracy result, and now basically this non-existence result is an immediate consequence if we put together what we learned in the last two videos. So since I have no type 3 critical points, I can repeat the proof that we saw in the last video, because there I have to again only to analyze this gamma star p, which is also basically has the same properties as gamma star in the case of p equals 2. And then one can see above the height of this inflectional elastica, which is h star of p here, and it can be written down what it is, but this shouldn't matter too much for this talk. If this cone obstacle is bigger than this height, then no minimizer can exist in M of psi. And the reason, again, is that this graph property is lost and that we observe vertical slopes there. And yeah, what I also should say, I have told you that it's sharp. So this result is sharp in the sense that in the if you minimize in the following set. So if you minimize among all functions in M of psi that are additionally symmetric, that one unfortunately needs to impose for that to be sharp. And it's difficult to show in a way because we are dealing with a first order problem. For small obstacles, we actually have shown that the minimizer is always symmetric, but we cannot show that at this point for every obstacle. So we minimize now in MSim, and if it is sharp in the following sense, if we take psi of 1/2 to be less than h star of p, then a minimizer in this class exists. So that is why it is sharp. So if we take psi above this, psi of 1/2 above this threshold, then there does not exist a minimizer. Whereas if we take psi of 1/2 below this threshold, then there exists a minimizer. That is what one can say here. Great, so this is what I wanted to remark there, that this result is actually sharp, and the reason is of course also that those computations in this article are very sharp. And now we have some questions, like two questions that we should maybe discuss. First question is, why does the Euler-Lagrange equation take such a nice form? And second question is, actually, about the strong maximum principle issue, we had a weak solution of this equation, maybe with a minus here, I'm sorry. Can one apply the strong maximum principle to weak solutions? That we should also that is maybe also of independent use, so we should talk a little bit about it. So first of all, why does the Euler-Lagrange equation take such a nice form? Basically, this becomes obvious when one rewrites the energy as the following: integral from 0 to 1 g of u prime prime to the power of p, where g is this function. So this is a way to express the energy. And if one takes a multidimensional equivalent to this energy, one would maybe write it down like so. The integral over omega over the absolute value of the divergence of g of grad u integrated to the power of p. So this one prime becomes the divergence, this other prime becomes the gradient. And for those types, it is sort of more obvious to see why one can make an interesting substitution there because of the following computation. So if I compute the derivative of this energy at a point phi, then what I get, first I have to take the derivative of the p's power here, and then I have to take the linearization of this divergence expression here, which is basically the derivative of G, like the Jacobi matrix, evaluated at the gradient of U, times the gradient of phi. So that's how I can compute this derivative of this energy. And now, if one makes a substitution here, W equals the negative divergence of G of nabla U to the p minus 2 times the divergence of G of nabla U. And this is exactly Euler's substitution. This is exactly what you can substitute there. Then your Euler-Lagrange equation takes your derivative takes the following form. So this just becomes W, and then the rest you simply copy. And if you now integrate by parts formally, like you shift the divergence over to the W, then you get this expression, at least if this W is regular enough, but this W is exactly what you get if you perform this Euler substitution I already gave to you, so it is definitely regular enough. Then I have this expression, and if I now shift this matrix over to this one side, I really get an elliptic operator here, because so if at least if the G of nabla U transposed is uniformly elliptic, this will be an elliptic operator for W, and this is what we profited from. So if dg of nabla U transposed is uniformly elliptic, then this operator is elliptic and second order. And so this is basically the whole trick behind it, how one can come up with such substitutions in case of energies that take this form. And so this is what one can do basically to study energies of this form in a very general way, and this is the origin of Euler's substitution and the structural reason why it applies. And if you now plug in what G is, and if you look at this W, you will exactly come up with the same term that I showed to you there as Euler's substitution. This dg here in our case turns out to be uniformly elliptic, which is great. Okay, and the other remaining issue is the strong maximum principle that I applied during this proof that I gave to you. Let's discuss a little bit about it, because then this proof is entirely settled and there's like no doubt remaining about this proof, hopefully at least. So what is the situation? We have a weak solution here, integral 01 a of x times w prime of x times phi prime of x is bigger or equal to 0 for some a which is c1 and bigger than 0. And we also know that w at the boundary equals 0. And the claim is now that either w is positive on 0, 1 or w is identically equal to 0. And so one needs here a strong maximum principle. This would be the statement of the strong maximum principle for weak solutions, as I already told you. And actually such a weak strong maximum principle is known or was studied by Littmann in 1959. However, what was the problem there is that one has to require more regularity for those coefficients. We have only less regularity than required there for the coefficients. The coefficients are required to be C2 there, so that we cannot immediately apply, but one can sort of apply that. This is also a result, let me emphasize that holds true in arbitrary dimensions. Here we only need it for one dimension. But still, it is not entirely applicable because the coefficients are not regular enough. So we have to come up with a new technique for this one-dimensional setting with less regular coefficients. And I will quickly go through the proof basically. of this one. So if we suppose that W is not identically equal to 0, then we have to show that it's bigger than 0 in the interior. And first, what one can learn from this equation in one dimension is that A times W star equals a monotone decreasing function. This is actually an immediate consequence of the Rees-Markov-Kakutani theorem, if you know it. But in any case, even though you cannot really perform an integration by parts here, it is enough to conclude that this AW star is a monotone decreasing function. And by the way, W is just a shorthand notation of W star. And now what does this mean? Since A is positive, the sign of W prime coincides with the sign of M, and M, since M is decreasing, it can only change from positive to negative. So basically I have now three regions, one region where W prime is positive, then in a region where W prime is 0, and then a region where W prime is negative. Another thing is not possible. And I have to emphasize also, all of those three regions may be empty, right? Because this decreasing function doesn't have to take any of those values. It can as well take only negative values or something. So all of those three regions could still be empty. That's why we choose here C and D. So the boundaries of those regions to be with 0 included and also with 1 included. And then what one can however show that the positivity region and the negativity region are not non-empty. So this is because we can show that C is positive and D is smaller than 1. Because if C equals 0, so if this region is empty, then you have only two regions here remaining, and in both of those two regions W prime is less or equal to 0, right? And if W prime is less or equal to 0, then W is decreasing. But the problem is W takes two equal boundary values, namely 0, it attains 0 at 0 and 1, and a decreasing function that takes the same values at 0 and 1 needs to be constant between 0 and 1, so W is identically equal to 0 there in such a case. But this is a contradiction, since we assumed that W is not equal to 0. And in the same way, one can show that D is smaller than 1, yeah? So C equals 0 was ruled out like so, and D equals 1 can be similarly ruled out, because then one has only those two regions left, and further and so forth. Now what we know is basically that this positivity around 0 happens, and this strict negativity happens around 1. And then we can use the fundamental theorem of calculus, basically. If we integrate, so say between 0 and D, then W is just the integral, since W of 0 is 0, from 0 to x over W prime. And W prime is positive in a neighborhood of 0. So whenever I plug in something positive there, I get positive values. So between 0 and D, I only collect positive values or 0 values here, but initially they are positive. So W is then definitely positive. Between D and 1, I can argue with this negativity in the neighborhood of 1, because I can write it as W of x minus W of 1 and write this as such integral, and therefore this is also positive. And this implies that W is positive in the interior 0 and 1, and this is basically what we wanted to show there. All right. So now we have the strong maximum principle for weak solutions, and with this I thank you for your attention. Bye bye.